Right, hello. So my name's Byron. I work for a company called Bluefruit Software. We're based down here in Cornwall in Redruth. We provide an embedded software development service. So we write software for other people. We don't actually have our own product. We introduced Agile practices in 2009, and since then we've delivered roughly 30 projects of varying sizes, some of them being only a couple of weeks, some of them taking several years. So for this talk, I'm not going to focus too much on the actual TDD cycle. There's been plenty of talks on that. I'm going to talk about the bits I'd like to have known after I've been to one of those talks. So how to apply this to my domain, and for me, that's specifically the embedded domain. And I'm going to be a little bit brave, and I'm going to take questions as I go, so it may throw my timings completely off. So what do I mean by embedded software? So embedded software is something that doesn't run on a desktop PC. It's software that runs on microcontrollers. So for us, the systems we're developing on are usually single core. They're somewhere between 8 meg and 200 megahertz processor frequency, anything from 256 bytes to 512 kilobytes of RAM, and up to about 250 kilobytes of flash, so that's our maximum code size. To give you an idea of like the latest Samsung phones, they're 2.15 gig, they have 4 gigabytes of RAM, and nowadays the average Android app is actually 18 megabytes. So hopefully most of you are familiar with the TDD cycle. Start off, write a failing test, run all your tests and see the new one fail, make a small change to make it pass, run them, see all of them pass, hopefully, refactor to improve your code and your tests, and lastly run again just to make sure you haven't broken anything. So probably less well known is the first mnemonic. This defines a set of criteria that your unit test should have. So firstly, they should be fast, they should run quickly. If they're slow, it creates a barrier to the developers actually running them, and they're going to run them less often. They should be isolated. So this usually means two things. Firstly, the test should isolate the cause of the failure. So developers shouldn't have to go and try and work out what actually caused the test to fail. It should be obvious from the test name and the assertion message. And tests should also be independent from each other, so you should be runnable in any order. There shouldn't be any dependencies between them. They should be repeatable, so the test should give the same results every time. There are lots of reasons tests can fail intermittently, especially for us depending on hardware which is outside of our processor, so something else on the PCB can cause problems. It may not always return the same value every time, and it will cause the test to fail occasionally. So this means we actually can't depend on the external hardware in our tests. You also shouldn't have any non-deterministic behavior in your tests, so don't start things like threads or spawn other processes in your tests. Tests should be self-verifying, so they should indicate pass or failure by themselves. There shouldn't need to be a human there deciding if the test has passed or failed. And lastly, they should be timely. So for TDD, this means that the test should be written before the code. If you're doing some other testing practice, it's just a good idea to keep them written. Write your tests close to when you write your code. So to show how we achieve the first criteria, I'm going to talk about where we run our tests to keep them fast, how our TDD style affects the verification of our tests. I'm going to show some examples of how we insert test doubles and how this keeps our tests isolated and repeatable. And finally, I'm just going to have a quick look at some of our other testing practices that we get as a bonus from this. So when we started TDD, we first needed to decide where we're going to run the tests. And we started with what seemed like the obvious option, to test on the target. And this actually worked really well for our first couple of projects, and it worked well for the first few months of our third project. But as our code base began to grow, this process started slowing us down. So we did some analysis of what was slowing the developers down, and we had a repeated step which was taking a long time. So we found that deploying and running the tests was taking a long time, and it wasn't really adding in any value. We cared about the output of these steps, which was the test results, but it was the time it took to get them which was causing the problem. And as with anything that slows developers down, they started trying to optimize the process. So in our case, the optimization was writing larger tests. Larger tests have a knock-on effect that they require larger code changes to pass, and it increases the chances of bugs creeping into your code unnoticed. So for us, the biggest advantage of testing on target was that we actually got accurate test results, and it will work if you have a really small code base or a very fast deploy. So in our first 2 projects, we actually had a really small code base. When we start new processes, we try them out on tiny projects. For us, there are 3 main disadvantages, so I'm not expecting anyone to read all of this. It's there if you want to have a look at the slides later on. Most of the disadvantages were because we were relying on the target platform. So the slower feedback I've already covered. As I mentioned at the beginning, our systems generally have very limited code space and RAM. Our tests are going to be at least as big, if not bigger, than our code, and we have to deploy the tests, the code, and the unit testing framework. So unless you have a really small code base, that's going to be a problem. You're going to have to break it down. We needed a set of target hardware for each developer. So this could have been in the form of a development kit. When we're developing products, quite often the hardware is also in development at the same time. So it's quite often broken and doesn't necessarily give you the results you expect. It's quite often expensive. Actually, sometimes we've broken it or blown it up. So it can cause all sorts of problems relying on the hardware. So nowadays, we actually no longer exclusively run our tests on the target platform. So when testing on the target started causing us problems, we moved to testing on our development PC. This removed the problem of the tests deploying and running being slow, and we actually thought this was great. So we had the fast feedback we wanted. We no longer had code space and RAM problems. We'd removed the need for the target hardware, and our code had ended up more portable. So now we're having to dual target because we wanted to deploy to our target and run on our dev PCs. So we'd already done that porting already. We were also able to use language features, which our target compiler didn't support. So for those of you that don't work in the embedded world, embedded compilers tend to run a little bit behind their desktop equivalents in terms of language features implemented. So this was great for when we're doing our tests. It allows our tests to be a lot more expressive. There were, however, some problems. We were testing code on one platform and running it on a completely different platform. So occasionally we had all the tests passing on the dev PC, but they didn't work on the target system. So for us, this was usually caused by some sort of packing problem because of the work we were doing at the time. But the bugs became that much harder to find. We were running code less frequently on the target device, so the changes between the runs were much larger. We no longer had that nice small increment that made it obvious where things went wrong. And another possible problem is that you are able to write code that may not compile for your target. So we were writing in C at the time, so this didn't tend to cause us any problems. But with C++ 11 and 14 out and 17 coming out soon, there's a good chance you're going to use features which work on your development platform but don't work on your target compiler. So in the end, we settled on dual targeting our tests. So this is pretty common nowadays, and in order to do this, we used a modified TDD cycle. So we start as per normal. We write a failing test. We then make a small change and refactor. When all the tests have passed, I then compile using my target compiler. So this checks I haven't actually introduced anything that isn't supported by the target platform. At this point, if I have run my tests in the last 15 minutes, I restart the cycle. Otherwise, I deploy the tests to the target and run them there. So this ensures I haven't introduced something that only works on my development system and that only deploying every 15 minutes reduces the impact of the slow deploy and run on the target. So this still has the fast feedback we wanted. It also has a few other advantages. So we still have the more portable code. Compiling with 2 different compilers tends to pick up additional warnings. One may quite often pick up something which the other one doesn't bother warning you about. And we're able to run dynamic code analysis. So if we're using some sort of dynamic memory allocation, we can do the memory leak detection on our development PC. The dev PC compiler quite often has better dynamic code analysis than the embedded one. And it also allows us to run sanitizers. So I'll come back to them in a little bit. So there are a few disadvantages to dual targeting. So you're still going to need the target hardware. You can now only use languages which are actually supported by both compilers. So this isn't so much a problem if you're in C++, but if you're writing in C and you're using Visual Studio as your desktop compiler, then you're stuck with C89 features. You're also going to need to maintain 2 builds, but this can be minimized by using the same build system for both and just switching your compiler and your linker. So I mentioned sanitizers. Sanitizers are runtime checks which are added into your binary by the compiler. They can check for all manner of things from out-of-bounds access to uninitialized reads and undefined behavior. They're currently available in both Clang and GCC, but not all of them are available on every platform. I'm not sure about the availability in Visual Studio. So I use them when I'm running my tests on my development platform. But one warning is that they do slow down the execution of your code, some of them up to 10 times. So it's not a great idea to compile and leave them in your production code. So in order to demonstrate what they can actually do, let's take a look at an example. So this code allocates a block of memory on line 11. Line 13 then passes it to a sort array function, which instead of actually sorting it, frees the code on line 6. The main function then accesses the same block of memory on line 15, so we have what's known as a heap use after free. So if I actually compile this code and run it using the command at the bottom, would anyone like to hazard a guess as to what it actually does? They are 2 options. It won't actually be random, by the way, because that's it's calloc, not malloc. Yeah. So actually, on my system, running Ubuntu with Clang, that actually just outputs 0 to the console. So we've accessed memory after it's been freed, but there's no actual runtime check to check that that's actually gone wrong. So it just works. So if we turn on what's known as the address sanitizer using the command line options at the bottom and run the program again, then we get this output to the console. So there's quite a lot of detail there, and the first time you actually see one of these, they can be a little bit daunting, but a lot of the important information is in the top third of the message. Again, still quite a lot of detail, but when these are output, they're normally color highlighted on the console. My copy and pasting abilities into PowerPoint unfortunately failed at this moment. So if I highlight the important bits, then we can see more easily what this is telling us. So the first line is telling us what happened. So we've got a heap use after free and the address that it actually happened at. The next bit gives us more detail of what actually happened, so a read of size 4 and a stack trace to where it occurred, so in the main function of code.c on line 15. We're then told a little bit about where the data is located and a stack trace to the bit which freed it, so it's freed in sort array on line 6. And finally, we're given a stack trace to the code that originally allocated the memory, so it's in the main function of code.c on line 11. So using sanitizers when you're running your tests on your dev PC can give you extra feedback that you may not actually get from your tests alone. So how you split your project down is going to determine how easy it is to maintain and to test. So we use a simple layered approach. We develop it over time in vertical slices, and generally are something akin to these layers. And for us, the further we go down the layers, the slower our testing becomes because we're getting closer to hardware. We tend to have a very thin processor layer that we don't actually bother to unit test. So this layer only sets processor registers. We found it to be relatively ineffective to test. The tests end up pretty much mirroring the code, which is usually a bad sign. We try and keep the cyclomatic complexity of this code to be 2 or less. We try and keep coupling low, so the more coupling we have between the classes, the harder it is to actually test the code. And lastly, we try and stick to the solid principles. So I find single responsibility and dependency inversion the 2 most useful of the solid principles. Even if you don't know anything about any of the others, those two are really going to help you. I'm not going to go into any details on them here. That would be an entire other talk. There are loads of articles you can read on this, and there's also the Robert Martin book mentioned at the bottom, which is a very good source for it. So at some point, we're going to have, the unit we're testing is going to end up depending on hardware. So in this example, if I'm testing the BMA 150 accelerometer, and I set up the dependencies in the way they are for the production code, then I'm relying on the Raspberry Pi I2C. In order to keep my test repeatable, I need to remove that dependency on the Raspberry Pi I2C. So I need to decide two things. Firstly, what I'm going to replace the dependency with, and secondly, how I'm going to replace the dependency. So I'm going to replace a dependency with something called a test double. So test doubles are objects created to fulfill a dependency for the purpose of testing. I'm going to use the terminology that Martin Fowler uses in his Mocks Aren't Stubs article, although I think he actually stole it from a book in the first place. So the four most common types of test double we use are stubs or spies. So these provide either fixed returns from methods, or they record what parameters were passed into a method. Dummies are there just to fulfill a dependency in order to create the system under test, so they're not actually used in the test. Fakes provide a working version of a dependency, but in a fake way, so something like an in-memory EEPROM or an in-memory database. And the last test double we use is a mock. So these are pre-programmed with expected behavior, defined by a set of expected method calls, and the mock verifies that those method calls actually happen. So which type of test double we use depends on our TDD style. For what's known as classical TDD, we use stubs, dummies, and mocks. And for what's known as mockist TDD, unsurprisingly, we use mocks. So it's worth deciding what TDD style you're going to use. This is actually something I found out really late in my TDD adoption. I never really heard of this until a few years ago. So to illustrate the difference, I'm going to use the example from Martin Fowler's article, but rewritten for C++. So what I'm trying to do, I'm trying to fulfill an order object from a removable inventory, which is implemented by my warehouse object. And I have an example scenario. So given the warehouse has 50 apples in stock and an order for 20 apples, when the order's fulfilled, then our warehouse will have 30 apples in stock. So we're checking that when that order gets fulfilled, we take the right number of things out of the warehouse. So classical TDD uses state verification, and there are two kinds of objects in our test. So the first kind is the system under test, in this case an instance of the order class called target. And the second kind of object is the collaborator. So these are dependencies of the system under test. So in this case, it's an object that implements the removable inventory interface. It's required to fulfill that order. And I'm using a removable inventory stub object as the collaborator to fulfill the dependency. Whether the test has passed or failed is then verified using either the state of the system under test or one of its collaborators. So in this case, it's using the collaborator. So classical testers only care about the final state of the system, not how that state was actually achieved. If it's practical, then you can just use the real object as a collaborator. So the system under test is going to be exactly the same. This time I'm using an actual warehouse object as the collaborator, and I'm setting it up with an initial inventory. And lastly, I verify the final state of the warehouse collaborator is what I expected. So testing using real objects has the advantage that you don't need to create test doubles to actually run the tests. And this means that classical testers tend to have a slightly broader definition of what they mean by unit. There are, however, some disadvantages to testing in this manner. So code changes that actually break the logic of your system tend to fail a larger number of tests. It's not a problem if you're only making really small code changes. It's going to be obvious which one caused the problem. And testing in this way can also lead to a slight sacrifice of encapsulation for testability. or adding in methods to check, verify the test. So in this example, my warehouse object is providing a method called how many in stock. So that isn't actually needed for any of the other functionality I've implemented so far. It's only there to verify the test. So the other style of TDD is mock-is TDD, and mock-is TDD uses what's known as behavior verification. The system under test is the same. This time I'm using a mock object to implement the removable inventory interface as the collaborator, and I've implemented it using Google Mock. So mocks tend to be quite long-winded to write by hand, so it's a good idea if you use some sort of framework to do it. The real difference here with the mock-is style is that you specify the behavior that the collaborator expects. So here I'm saying that there must be a call to has inventory and then a call to remove inventory. So mock-is testers care about how the behavior is implemented, and they think about it while they're writing the tests. Specifying that behavior in your tests couples your tests to your implementation. So it does mean that refactoring can be harder later on because your changes are more likely to actually break a test. So in summary, classical TDD has the advantage that it doesn't specify how the code works. It only checks the final state, and this makes refactoring easier. The disadvantages are that single code, incorrect code changes can break a lot of tests, especially if you actually use the real objects as collaborators, and there can also be a trade-off between encapsulation and testability. The advantages to mock-is TDD is that incorrect code change only breaks the tests which actually relate to that code change. And mock-is TDD makes you think about how you're implementing the actual code when you're writing your tests. Some people see this as an advantage, some as a disadvantage. But the main disadvantage is that tests are coupled to the implementation, so that makes refactoring that much harder. So nowadays, I tend to switch my TDD style depending on which layer I'm testing. So I use mock-is TDD when I'm testing anything which relates to hardware. This is because the behavior of my code is generally determined by how I'm going to interact with that hardware. So if I have something like an SPI device, I know I need to set chip select line low, do some reads or writes, and then set the chip select line high. So I find having that behavior specified in the test makes the test a heck of a lot clearer. And I use classical testing for everything else. So I prefer my tests not to be coupled to my implementation so that I can refactor that much more easily. So I've looked at what I can replace dependencies with, but how can I replace them, and what effect does that have on my code and tests? So in C and C++, there are 3 times you can insert test doubles: at compile time, at link time, and at runtime. And there are various techniques you can use at each point. So this isn't an exclusive list, by the way, this is just a few examples. I'm going to show examples of these 2 techniques. So one of them is a technique we use all the time, and is probably the most common way of doing it in C++. The other is something we use specifically to counter problems in embedded systems. So to illustrate the difference, I'm going to use some code I wrote for a course I ran teaching university graduates Agile software development practices. We set them a project of developing a monitoring system that would track how a person's arm moved during various sporting activities. The system used a BMA 150 accelerometer and various other sensors to monitor motion, and the target platform for this was a Raspberry Pi. So the BMA 150 is BMA 150 accelerometer is an I2C device. You don't really need to worry about what I2C is, it's just a serial protocol. So the code and tests were set up as follows. The system under test was the BMA 150 accelerometer driver, and it has one dependency, which is an I2C port. When I'm testing, I want to use a mock I2C and the tests. And when I'm building the final application, I want to use a Raspberry Pi I2C and the actual application code. So the first test double insertion technique I'm going to talk about is C++ interfaces. So this is by far the most common technique we use when we're developing in C++, and we use it for inserting test doubles throughout our code. So when using C++ interfaces, the dependency interface is an abstract C++ class whose methods are all pure virtual. So in this example, it declares 3 methods. These allow setting the device address, reading from the device, and writing to the device. The mock I'm going to inject is derived from the I2C interface. It defines the methods. It defines the methods which need to implement the interface, and as it's a mock, it needs to provide a set of methods to set the expected behavior. And lastly, it needs to verify that all of the methods that should have been called have been called. So for this, it has a verify method. Providing the insertions in the verify method don't throw an exception, then I like to call the verify function in the destructor of the mock. So this ensures that the mock always verifies when it goes out of scope. If I forget to call the verify method, it doesn't actually matter. So now I have everything I need to write my test. So first I create an instance of my test double. I then provide it with a set of expected method calls. Next I create the system on the test and inject the test double. So this is where I'm inserting that test double I have control over, so I can verify if my test has passed or failed. I then exercise the system on the test, and finally, as the method actually returns some values, I check they're correct, and the mock will automatically verify that all the expected method calls have happened when it goes out of scope, so when it hits the end of the test. So now I have the test, I can actually write some code. So the BMA 150 accelerometer depends on the I2C interface, so I need to supply it with an object which implements that interface. So here I've used a very simple dependency injection technique in the constructor of the class. So this is the code that actually allows me, or is actually accepting that test double being inserted. When you're doing this and you're running it in your actual code, you need to be careful of object lifetimes and make sure that the I2C doesn't get destroyed before the BMA 150 accelerometer. Well, that causes all sorts of fun. The BMA 150 accelerometer object can now use that injected dependency when it's reading the acceleration. So the BMA 150 accelerometer is not coupled to a specific implementation of the I2C interface. I'm free to provide it with whatever I want. So using C++ interfaces is the easiest method of test double insertion in C++. There are, however, a couple of disadvantages, although they tend to be minor. So virtual function calls are slower than calling methods directly, and this can be a problem, especially when you're in time-critical bits of the code. And the V table caused by those virtual functions is also going to take up space in either ROM or RAM. So on the really tiny systems where we've got very limited space, that can cause problems. So the next technique I'm going to talk about is linking other object files. So we use this when the problems with speed or code space have become a problem. So it's using the time-critical bits of the code. The example I'm going to use here is done in C, although this works exactly the same in C++. So with this technique, the dependency interface is just the function declarations of the I2C code. We don't want any virtual function calls. The system on a test is just going to call its dependency directly. The trick with this technique is that I switch the code implementing the dependency at link time. So the BMA 150 accelerometer object is common to both files, but when I want to test the code, I link in the mock I2C and the tests, and when I want to write the final application, I link in the Raspberry Pi I2C and the application code. So the important part here is that these two files contain different definitions of the same functions. So this can be easily achieved using a make file. When I want to build the tests, I link the mock I2C object file and the tests object file. So this is actually where I'm inserting the test double I have control over. And when I want to build the application, I link the Raspberry Pi object, Raspberry Pi I2C object file and the application object file. In both builds, I'm linking the same BMA150 accelerometer object file. So I'm testing as close as I possibly can the code that's actually going to end up in the final application. So the mock needs to implement the dependency interface. The key here is that the method definitions must match the method declarations from the dependency interface header. Next are the methods that allow me to set the expected behavior. And as with the other technique, I need a verify method to check that the expected behavior has actually happened. Now I'm actually going to have to call this directly in C, as C provides me with no method of tying a function call to the scope of the test. So the test follows a similar pattern to the previous technique. The expected behavior is specified. The real difference here is that there's no need to inject the collaborator. That's already been done at link time, so it's going to be called directly. The system under test is exercised. We then verify the method to ensure that verify the mock to ensure that all the calls have actually occurred, and then the return result is checked, as in the last one. So as the dependency has been injected at link stage, there's no need to inject it in the actual code. So the system under test is able to call the dependency directly, and this means that there's no virtual function calls either slowing down or taking up code space or RAM. So inserting test doubles by linking other object files removes the need for virtual function calls in time-critical bits of the code, and it saves on that extra code space. It does, however, add complexity to the build system. So just a quick summary, we use C++ interfaces for inserting test doubles everywhere, and we link other object files when those virtual function calls have become too expensive. So what else? So as I mentioned earlier, we're quite often short on hardware. So when hardware is in short supply, we use our build servers to run our tests on our target platform. Are you taking a photo of that just because for once it's always green? Yeah. So this is possible because we use Git as the source control management, and all of our developers have a fork of the code. Our build server then monitors all of those forks, and when a developer pushes a branch to a fork, the build server will download it, build it, and deploy it to target, and then run the tests. The developers can then either get a toaster notification or a notification in their IDE about the build results, or they can just look on the information radiator if they want to. So we have two different types of integration tests. So we have integration tests that check how our code interacts with hardware. So the photo shown here is an integration test setup I built for one of our projects. So these actually check that our code actually talks to the hardware correctly. Up until now, we've completely isolated the hardware, so we don't actually know if it's working. So these make sure that it actually works. And we also have integration tests which run in a simulated environment. So these check the interactions which can't be tested using the hardware, so things like error conditions. Generally, hardware is usually quite hard to make it go wrong, apart from when you don't want it to. And the final practice I'm going to talk about is how we speed up our system testing. So this is something we've been experimenting with for a little while. So we started experimenting with this technique because we had a problem testing one of our projects. Thanks, yep. So the project was from removing impurities from water, and because of this, it had processes that took hours to run. So you'd literally go up, press a button, and then it would sit there for hours, occasionally turning pumps on and off and toggling valves. And this actually slowed down some of our iterative feedback loops. So we have many layers of feedback loops to help us monitor our code quality and make sure we don't introduce bugs into our code. So the first feedback loop is the other person in our test, which usually gives us feedback within about 5 seconds. We run our unit tests at least once every 5 minutes. We run the integration tests approximately once every half an hour, so they take a little while to run. From when we submit code for code review to when we actually get feedback usually takes about half a day. Our system tests for our new code we introduced could take up to a couple of days, and this wasn't really ideal. This was caused by those long processes. But by far the slowest feedback was provided by our regression tests, which sometimes could take approximately a week to run, even if they're automated. Our regression tests didn't normally find bugs in the lower level drivers, so they were very much picked up by our unit and our integration tests. It found bugs where we changed something in our application layer, we changed some sub-process which was used in loads of larger processes, and that change wasn't meant to be in all of them. So this is one of our simpler system tests. And running it, we can run it either manually or automatically, and it's normally run with the code compiled as it is on the right. So in order to get the faster feedback, we change what the test actually runs against. So we remove the code which interacts with the hardware, and we replace it with a fake BSP layer. So this fake BSP layer is usually the test doubles or mocks or stubs that we created for our unit tests. So these tests now run purely on the development PC, and this means that we receive feedback from our system tests in a much shorter time. So we've got that quick feedback back. The one caveat to this is that we only use this technique to actually check if our code is broken. As we're not actually running it against the real system, we can't say that it's definitely working, but it is a good indicator that stuff is broken. So, in summary, I've talked about how we keep our tests running fast by dual targeting. I've had a look at how we vary our TDD style and how this affects the verification of our tests. I've looked at how we insert test doubles and how that keeps our tests isolated and repeatable. And I've had a brief look at some of our other testing practices. So that's it. Thank you for listening.